Can people hear me in room 230?
Yes, we hear you.
Good.
Yep. I think we're all ready in the room. So, yep.
Great. Okay. So next talk, we have Ling, who's going to tell us about remarks on the cosmological constant appearing as an initial condition for Milne-like spacetimes.
Okay. Thank you, Jerome, and I want to thank the organizers for inviting me here, giving me this opportunity to speak. So I'm going to talk about the cosmological constant appearing as an initial condition for Milne-like spacetimes. Milne-like spacetimes are spacetimes I am obsessed with. So, okay, outline. Okay, so first, I'm going to discuss Romanian Milne-like manifolds. And so Milne-like spacetimes are Lorenzian manifolds, and Lorenzian geometry is hard, but what's easy is Romanian geometry, easier. And so this, the fact that Milne-like spacetimes, they emit extensions through the Big Bang, this actually has a nice Romanian analog, and I think it's nice to see the Romanian analog first. So we'll do that, and then, I guess I have the pointer here, and then we'll discuss FLRW and Milne-like spacetimes. So FLRW spacetimes are spacetimes that model the large-scale isotropy of our universe, and Milne-like spacetimes are a subclass of FLRW spacetimes that emit extensions through the Big Bang. Okay, and then finally, three, I'll talk a little bit about the cosmological constant, why it appears in the Einstein equations, and then we'll get to the main result, which is showing that the cosmological constant appears as an initial condition for Milne-like spacetimes. Now, this isn't very hard to see for Milne-like spacetimes themselves. The main result is actually showing that this is going to remain true for versions of Milne-like spacetimes that are no longer isotropic or homogeneous. So we're going to take away any symmetry assumptions from these spacetimes, but we're still going to see that the cosmological constant will appear as an initial condition. And then finally, 5, I'll show how this fact that the cosmological constant appearing as an initial condition can have applications to inflationary theory via yielding a quasi-de Sitter expansion for the early universe. Okay. Before I begin, let me just make some conventions I'm starting off with. So manifolds we'll denote by M. I'm always going to assume the manifold is smooth, connected, Hausdorff second countable. I am interested in low regularity. The low regularity is all in the metric though. So we say a metric is ck if its components in any coordinate system are ck functions. And really, I'm only going to be interested in two cases, one when the metric is smooth and the other when the metric is continuous. And assuming that the manifold is smooth, we don't lose any generality, because if we're assuming a continuous metric, then we have to assume at least a C1 atlas. And it's a result that any C1 atlas actually contains a C infinity subatlas that's compatible with the C1 atlas. So if you had a C1 atlas to begin with, then you just say, oh, well, I don't want that atlas. I'm going to go to the smooth atlas and do all my work in the smooth atlas. So that's what we're doing. Okay, Romanian Milne-like manifolds. So definitions, a CK Riemannian manifold, MG is one where the metric is CK. Okay, I guess that wasn't too hard. So a continuous Riemannian manifold, pointer. A continuous Riemannian manifold, this M extension, G extension here, is called a continuous extension of a smooth Riemannian manifold if two things happen. The dimensions of the two manifolds are the same, and two, there is an isometric embedding of the original smooth Riemannian manifold M into the larger one, such that M inside the extended one is a proper subset, right? So in other words, you can say that you are an open submanifold of the extended manifold. And then finally, we say that MG is C0 inextendable if it emits no continuous extension. And proving things are C0 inextendable is actually fairly difficult. Okay, so here are just some basic examples. So here we're going to consider the smooth Riemannian manifold M is 0 infinity times R, and the coefficient in front of G is just 1 plus the square root of X, right? And so then you ask, does that have a continuous extension? Well, yes, you just define G extension just to be the Euclidean metric for negative X values, right? And of course, this will be a continuous extension, but it won't be a C1 extension because of the square root of X term. Okay, so that's an example of a continuous extension that doesn't emit or that doesn't have a C1 extension. an example of C0 and extendable Riemannian manifolds are complete Riemannian manifolds. So complete Riemannian manifolds are C0 and extendable. Whoops. And the proof uses the existence of length minimizers in arbitrarily small neighborhoods. So we know for smooth Riemannian manifolds that we have length minimizers in arbitrarily small neighborhoods using normal neighborhoods. This fact remains true in C0 Riemannian manifolds. So the proof, I'm just going to illustrate this proof very quickly. The idea would be the following. Suppose, yeah. So suppose, so we're trying to prove that a complete Riemannian manifold is C0 and extendable, so the proof is by contradiction. Suppose you actually had an extension, right? So, say again? Yeah, existence. No, I was confused. Okay, so so you have your smooth Riemannian manifold M, and then it sits inside isometrically inside a larger Riemannian manifold. This is M extension here, and then because you're a proper subset, the boundary is non-empty. So this is the boundary of M, and so there's a point on the boundary. Let's call that point Q, and essentially you can draw what is essentially a normal neighborhood, but not normal because you're C0. But you can have a neighborhood around here, this point, such that you can find for any point inside the manifold M, let's say P, you can find a minimizing curve from P to Q. Okay, but this minimizing curve is inextendable. So sorry, this minimizing curve within M has to be a geodesic because it's minimizing, and it's inextendable with M. And being inextendable with M implies that it has to then be complete to the one side, which means that it has infinite length. So this curve here has infinite length within side M, but you can have shown that you could have chosen this neighborhood so that you could have bound the lengths of minimizers here. So that would have been impossible. So this can't exist, and that would be the proof. So these are the types of arguments that one would use to prove C0 inextendability. Okay. Okay, so now let's talk about Riemannian Milne-like manifolds. So consider the family of warp product spaces. So 0 infinity times S2. And the metric here is dr squared plus a squared of r times h. H is going to be the round metric on S2. And a is just the warping function. It maps from 0 infinity into 0 infinity. And we're going to assume it's smooth so that this is a smooth Riemannian manifold. And we're going to make the assumption that the limit as a of r, the limit as r goes to 0 of a of r is equal to 0. And of course, the main example of this would be a of r is equal to r itself, right? In that case, we're just writing out the Euclidean metric in spherical coordinates, right? And so then this manifold then would be R3 minus the origin, right? It's isometric to Euclidean space minus the origin. And so the motivating question I want to ask is, well, what are conditions on a of r so that M emits a continuous extension through the origin, right? And clearly, there are some conditions, because if you just had a of r was equal to r itself, then you were Euclidean space and you emitted a smooth extension. But there are some conditions. So to answer this question, we're going to write out the metric at first in spherical coordinates, and then we're going to introduce these new coordinates, z and rho here. Oops. Z and rho, right? And they are defined as b of r times cosine theta and b of r times sine theta, where b of r is related to that warping function a of r via this expression here, and r naught is just some value in 0 infinity. And so when you do the calculation, it's not hard, in these new coordinates, what you find is that the metric within these coordinates looks like this. So notice that this is dz squared plus d rho squared d phi squared. This is just the Euclidean metric written out in cylindrical coordinates, right? And then you have a conformal factor out in front, which is a over b. So it's easy to see what would be a sufficient condition to get you an extension through the origin, right? What you would need is that you would need this conformal factor a over b to limit to a positive number as you go to 0, right? So you have this, you imagine you have these spheres, right? And this warping function a of r, it controls the area of the spheres. And if you control it in such a way such that this quantity a over b limits to a non-zero finite positive number, then you would get a continuous extension. Okay, so then this motivates the following definition. If a of r is equal to r plus little o of r to the 1 plus epsilon, for some epsilon bigger than 0, then we say mg is Riemannian Milne-like. And in that case, We have the following theorem. If mg is Riemannian Milne-like, then that conformal factor did indeed approach a non-zero finite number. It approached R, where R was that beginning beginning position in the integral for B. And so then we emit a C0 extension. And I should mention that it's very important that it's A of R is equal to R plus little of R to 1 plus epsilon. If it was some other constant, then this would correspond to a canonical singularity, and actually I'll show results where you couldn't have extended it in that case. Okay, so that was Riemannian Milne-like manifolds. So now let's talk about F. How A enters into the metric. Yeah, so right here, right? So A of R equals R is just Euclidean space, but we're saying essentially asymptotically as R equals to 0, something that looks like Euclidean space. But after that, it can do whatever you want it to do. Okay. So FLR.
They always do what we saw in the space, where basically the point is like a removable singularity somehow, or can it connect to something more exotic?
It can connect to something more exotic. I think that this was just a very special case. Okay. Okay, FLRW and Milne-like spacetimes. Okay, so let's just begin with the definition of a spacetime. I'm going to assume that people know the definition of a Lorenzian manifold. So a CK spacetime is a time-oriented Lorenzian manifold where the metric is in CK. So again, we're assuming that the metric components are CK functions written out in any coordinate system. Time-oriented just means we can make a continuous choice of a future, and that's usually dictated by some time-like vector field. So the main example would be Minkowski spacetime, which we're all familiar with, and then the time orientation would be dictated by saying that the vector field partial t in these coordinates is future directed. Okay, for non-zero vectors x in a spacetime, if the inner product of x with itself is negative, then we say it's time-like. If it's 0, it's null. If it's 0 or negative, it's causal, and if it's greater than 0, it's space-like. So if you have a time-like null or causal vector, then you can say it's either future directed or past directed, depending on the time orientation that you gave it. Okay, and then finally, one other thing that we will need is the time-like future. So given a point P in M, the time-like future of P is just a set of points Q in M such that there is a future directed time-like curve from P to Q, and my definition of time-like curve is going to be any one such that I plus a P is open. So I know that there's subtleties here, but I'm going to choose one that I plus is open. Okay. Okay, so these definitions essentially mirror the definitions in the Romanian setting. So we say that a CK spacetime, MG is one where the metric is CK. A C0 spacetime, M extension, G extension is a continuous extension of a smooth spacetime if the dimensions are the same. And 2, there's an isometric embedding such that one is a proper subset of the other. And then you are C0 inextendable if there is no continuous extension. Okay, so those are spacetimes, FLRW spacetimes. So FLRW spacetimes are warp product spacetimes. So the manifold is just an interval times sigma, where sigma is a space form. So it's a space of constant sectional curvature. And the metric G is minus d tau squared. So tau is the coordinate on the interval, and then H is the metric on the space form, and then A is your warping function, which we tend to call the scale factor in cosmology.
Eric?
Yeah.
How important is the form of H? You're saying this is FRW-like, so we would think in cosmology that H is homogeneous and isotropic. But yeah, what role does that play here? Could it be more general than that, in fact?
So okay, so in three dimensions, making the assumption that you're isotropic in 3 dimensions, this will imply that you have to have a space of constant sectional curvature, and that limits it to the ones that we're familiar with. That is like the sphere, Euclidean space, and hyperbolic space. In higher dimensions, there's actually something that can happen that's different. So there's other things you can consider. There's like the Fubini metric that would actually count because it's isotropic. But in 3 dimensions, it just limits to the case where H is either going to be positive, negative, or 0 sectional curvature.
Sure. So you're saying you need this assumption here for the following discussion as a whole.
Yes, yeah. So when I say sigma h is a space form, I mean that it's essentially, it's going to have constant sectional curvature, +1, 0, -1. But in the definition, we allow whatever topology that you want to consider, so long as you're a complete Romanian manifold. So for example, you could have had the torus, you could have had the dodecahedron for hyperbolic space, you could have had, you know, quotients of S3, right? RP3 or something.
Yeah, sounds good.
But when we define Milne-like spacetimes, it's going to be very important that the space that we consider is going to be the simply connected one.
All right.
Okay.
Thanks.
Okay. So the co-moving observers in these spacetimes, these are the integral curves of the vector field U, which is partial tau in these coordinates, in co-moving coordinates. And physically, they model the world lines of the galaxies, stars, dust in the universe, but they don't model radiation because radiation travels at the speed of light. Right? So co-moving observers are the time-like curves, right? And they're supposed to model, the way one envisions it is that they model maybe a particular galaxy or something in the universe. If the limit of the scale factor goes to 0, then tau equals 0 is called the Big Bang. And then finally, if A of tau is equal to tau plus little of tau to the 1 plus epsilon, as tau goes to 0, for some positive epsilon, and sigma h is the unique simply connected hyperbolic space with constant sectional curvature -1, then we say Mg is Milne-like. Okay. And so this theorem here basically parallels the theorem that we saw with the Romanian version. I mean, the proof is not any more difficult. So if Mg is Milne-like, then Mg emits a continuous extension. And the proof is as follows. You write out the hyperbolic metric in these co-moving coordinates, and then you introduce these new coordinates, little t and little r, and these were analogous to the cylindrical coordinates z and rho that we introduced. It's just that before we had a cosine, and now we're going to have a hyperbolic cosine, and before we had a sine, and now we're going to have a hyperbolic sine, right? And so then where b is, again, this same function, b of tau is equal to this exponential of this integral for some positive tau naught. And when you write out the metric in these coordinates, what you find is that you are then conformal to the Minkowski metric written out in spherical coordinates, right? And so the same argument as before says that all one needs to do is find sufficient conditions on this conformal factor a over b in order to get a C0 extension, right? So if you find sufficient conditions on this conformal factor such that this limits to a non-zero positive number, finite number, then you would have a continuous extension. And in this case, it will extend continuously through the light cone at the origin, which is now the origin in this spacetime that's conformal to Minkowski spacetime. So this is what the picture looks like. The shaded region represents the original Milne-like spacetime, and it's foliated by hyperboloids, right? Because it was the hyperbolic choice of FLRW spacetimes. So these are the foliations of the spacetime, and what happens is that you're limiting down to the cone in Minkowski spacetime, and you can extend continuously through the cone. So this is analogous to the Romanian setting, right? In the Romanian setting, you had spheres that were going down to a point, foliating the space until you reach down to a point, and then you could extend to the point. Here you have hyperboloids that foliate the spacetime, and then you extend down to the cone. And
Right, that brings me back to my question. In the Romanian setting,
yeah,
if I have an A that is not just R, but R plus some correction with the property that you want it below, is it possible that the extension is not to the point, but something more exotic?
Is it possible that the extension? So that's a good question, because it's a question about uniqueness of extensions almost, right? So in these coordinates, in the coordinates that I introduced there, then yes, it could have only been a point, and that I'm pretty confident I can prove, but you would need to use some Romanian geometry to prove that. But it doesn't say what would happen in other coordinates, right? In other coordinates, something crazy might happen, and one would have to eliminate that type of scenario to say that it could have only been the point there.
You don't have an example of something like that?
No. Mm-hmm. But yeah, I think that's an interesting question to say that this could have been the only thing that could have happened. Okay. So note, so this is just very recent work. So note that this assumption on the scale factor with the epsilon, I want to say the whole thing out every time. So with the epsilon, it implies it without the epsilon. So when you have the epsilon, you have A of tau equals tau plus little o of tau. So three natural questions arise. So one, is A of tau equal to tau plus little o of tau sufficient? And what Ana Chiara Pubello and I showed was that there are examples of scale factors that satisfy this condition, A of tau is tau plus rho of tau, such that the metric does not extend continuously through the light cone. So there are examples that you don't extend continuously through the light cone, so you're not sufficient. Is A of tau, then you can ask, well, is A of tau equal to tau plus rho of tau necessary? And what we showed is that if the metric does extend continuously to the light cone, and the limit of A prime exists as tau goes to 0, then you had to have had this form here. So in some sense, it is necessary, but we had to make this extra assumption that the limit of the derivative exists. And there are examples where that doesn't exist, but you would still satisfy this condition. So it's not, so we don't have it fully yet. But this also does rule out the conical singularities that David Garfinkel was talking about in case of the Romanian setting, because in that case, you wouldn't have had something like tau plus rho of tau, but you would have had something that was like a constant times tau, where the constant was less than 1. In that case, you can't get an extension. You could not get the proof that we have here says that you wouldn't be able to extend within those coordinates. And then finally, now that we know that the answer to 1 is no, then the question 3 is the epsilon in this expression necessary? And the answer to that is no. So there are examples of scale factors satisfying this limiting condition, but A of tau is not equal to tau plus little o of tau to the 1 plus epsilon for any epsilon, such that the metric does in fact extend continuously to the light cone. So really, all that matters is that A over B limits to some non-zero finite number, and you could have, and that will always happen if you have it with the epsilon. It'll sometimes happen if you don't have the epsilon, and sometimes it won't happen. Yeah, this would have an exact analog in the Romanian setting.
Should be easier, I guess, right?
Yeah.
Should be,
I mean, the intuition is easier, but the math would be exactly the same, in fact.
There's some sharp criterion that like 1 over the error term is integrable.
Say again?
Like before, you had the formula for B, so you have to integrate
1 over A. Yeah.
1 over A minus tau. So that. So I'm wondering if there's a sharp criterion like this integral exists and all that you can extend it.
So we said, yeah, so sorry, we have a result that says that if you extend through the light cone if and only if the conformal factor B over A converges to a non-zero finite number. And you can write, because B over A, if you take the log of it, then you can start looking at the integral. And then it becomes it's a if and only if a certain integral converges. So it is sharp in that sense, but asking when that integral converges is then also another math question, which is something that we address in this paper too. So.
Eric, sorry, just a quick question, because sometimes there's a terminology difference between us. So hyperbolic, you mean the sectional, the space manifold is hyperbolic, right? Not the.
Yeah. When I say hyperbolic, I mean the choice of FLRW spacetimes where you have k equals -1.
Okay. So this was not proven, I guess, for positive or zero curvature.
Yeah. So well for positive and zero curvature, we don't have results for extending. I mean, for a finite value of tau, but Jerome, right, with Deslik has results when you go down to t minus infinity in the flat case.
Yeah. So that's I guess for some reason I thought it was also for, but yeah, you're right. I guess it doesn't apply to positive.
Yeah. So no, so the results here are only for the hyperbolic case, and in fact we have so my old PhD advisor Greg Galloway and I, we have results that say that in the spherical case and the Euclidean case, so k equals +1 and 0, if your Big Bang occurs at a finite tau value, so not minus infinity like what Jerome considers, but at a finite time value, then you cannot, and your extension has spherical symmetry, then you couldn't extend it. So I should say you cannot extend it to a manifold that has spherical symmetry. It might still be possible that there is an extension, but it'd be really weird because the extended manifold couldn't have spherical symmetry. Yeah.
Thanks. That's interesting. Yeah.
Okay. So those are Milne-like spacetimes. So now let me briefly talk about the cosmological constant. Okay. So an important aspect about FLRW spacetimes is that they satisfy the Einstein equations with a perfect fluid. And what that means by satisfying the Einstein equation with a perfect fluid is it means that there's a vector field U, And there's functions rho and p called the energy, density, and pressure, such that the Einstein equations take this form. So that's the definition of solving it with a perfect fluid. For FLRW space, you just take u to be partial tau. And this u star here is just the one form that's metrically equivalent to the vector field u. So I say that right here. Yeah, u star is just the one form metrically equivalent to u. And then for FLRW spacetimes, this equation is satisfied with rho and p obeying these equations here. So if you just ignoring the physics right now, where rho and p come from, take in a scale factor a, right? Then your FLRW spacetimes will satisfy the Einstein equation for the perfect fluid, where u is this, where u is partial tau, and rho is given by this expression, and p is given by this expression. And k equals +1, 0, or -1, depending on the space form that you're considering. Now, irregardless of the value of k, if you add up these equations for rho and p, what you'll find is Friedman's second equation here, a double prime. And so this equation is going to be very important for the coming discussion. Okay, so now let's talk about equations of state, and this more belongs in the area of physics. So to close the Einstein equations, so to solve the Einstein equations, to solve for the scale factor, one imposes an equation of state, and what that means is a relationship between rho and p, and it's usually determined via some thermodynamic principles. Common equations of state are when you are considering dust, in which case the pressure is 0, or when you're considering radiation, where the pressure is 1/3 the radiation. And so before there was dark energy and inflationary theory, people built their cosmological models by assuming some mixture of radiation and dust. And so what happened in the hot Big Bang model was that your universe started off in a radiation state, and then it transitioned into a dust state. But what's important is that of these two equations of state, both p dust, for both dust and radiation, the scale factor is going to be negative. And again, the scale factor, the acceleration of the scale factor is negative. And this follows from Friedman's second equation, right? So Friedman's second equation is here. If you use either of these equations of state, so just take dust, so p is 0, then you have rho. And if you're assuming rho is positive, then the scale factor, its acceleration is negative. Okay. However, what's interesting is that observations in the 90s showed that the scale factor is not decelerating, it's actually accelerating. So given our current cosmic time right now, they found that the scale factor is actually accelerating. So what's interesting about this is that our physical matter models don't allow this, right? So you need something else to actually say what is causing the acceleration, and the easiest thing to include into the Einstein equations is a cosmological constant that can account for this, right? So to explain this effect, cosmologists suggest that there is an invisible dark energy throughout the cosmos, and let's just say that it has an equation of state given by rho is equal to -p. So if you consider an equation of state where rho is equal to -p, it's a constant where that's equal to lambda, the cosmological constant, then it's easy to see that a double prime will be positive, right? So you can get an accelerated expansion. So I think it's important to note here is that I mean, why do we believe in the cosmological constant? I don't think we believe in it necessarily physically, because there are these physical matter models that do this. It was kind of forced upon us by observations. The observations are telling us that the scale factor is accelerating, and we needed something to account for this. And I think the easiest thing to account for would have been a cosmological constant. Okay.
Observations, we need to compute acceleration for the scale factor. Obviously, we only have observations for one instant in time. Oh, but I guess looking back further into the universe, you get something from earlier instances. Yeah,
so I mean, there's two ways that they calculate it right now. I mean, the first, when it got public, it was by doing type 1a supernova, right? And I don't actually fully understand what they did. So I think probably Jerome and Gazelle would probably have a better understanding of what they did. But something I do understand better is that in order for it to have matchings between the C and B, what we observe in the C and B, and what the cosmic microwave background radiation, and today, you needed to have a cosmological constant term in the mixture to make things work. So and they already, before the observations of the type 1a supernova, these people were already converging on that idea. So people were already thinking like, oh, there needs to be something like this happening before the type 1a supernova were observed. Okay, so now let's talk about how the cosmological constant appears as an initial condition for Milne-like spacetimes. This is not a very difficult proposition. So assume we have a Milne-like spacetime, so it satisfies that asymptotic condition on the scale factor, so you limit it tau. And just for simplicity, let's assume it's analytic, right? So if it's analytic, then you can write it as a Taylor expansion, but the first term is tau, so you have all these other terms. And so then it's an easy proposition, just a limit problem, that if you set C2 equal to 0, then when you take the limit as tau goes to 0, rho of 0 is equal to minus p of 0. And this is not a hard problem. I mean, this is something that you just plug it into these expressions for rho and p, and out pops the fact that rho has to be equal to negative p at tau equals 0. Okay, so it happens for Milne-like spacetimes. So now let's go to our main result. And the main result is we want to, the motivation is to generalize the previous proposition that this equation of state, so let me go back. This I'm phrasing as the cosmological constant appearing as an initial condition because the equation of state at the Big Bang satisfied by rho and p is that of a cosmological constant. It's not saying that the cosmological constant itself is there, but just that the equation of state satisfied by rho and p is that of a cosmological constant. And what I want to do is generalize this fact to spacetimes that share similar geometrical properties with Milne-like spacetimes, but are not homogeneous or isotropic. So this is the motivation. Generalize the previous proposition to spacetimes that share this geometrical properties, but without any symmetry assumptions. So two important properties that we will want to keep are the following. So the first is that we want to still assume that the FLRW spacetimes satisfy the Einstein equations for the perfect fluid. So we're still going to assume that there's a special vector field U, there's an energy density rho, and a pressure P, such that the Einstein equations take that special form of a perfect fluid. And the second thing that we want to assume comes from an observation of what happens to the co-moving observers in Milne-like spacetimes. So the co-moving observers, they are the integral curves of U is equal to partial tau. And for Milne-like spacetimes, because the co-moving observers, they're orthogonal to the spatial slices, right? They're orthogonal to the hyperboloids. And being orthogonal to the hyperboloids mean that they all look like this, right? And so this is very similar to how in like the Romanian setting, you could ask, what are the integral curves of the partial R vector field? The integral curves of the partial R vector field are all going to emanate from the origin. And the same thing is happening here. So this assumption that all the co-moving observers are all emanating from the origin is something that we also want to assume. Okay, so here is the setting. We're going to consider the existence of a continuous extension of a smooth spacetime such that M is equal to the time-like future of the extended spacetime given some point in the origin, right? So essentially, I mean, the picture looks like this. M is equal to the time-like future of some point to some extended spacetime. And then before we can get to the main theorem, I have to make some definitions. So consider a smooth function f. Consider a smooth function f on M into R. Then we say that f extends continuously to M union the origin, provided one can find a continuous function on M union the origin such that its restriction to M is f itself. And of course, the topology on this set M union O is just the subspace topology inherited from the extended manifold. So that's what it means for a function to extend continuously to M union the origin. More generally, let T be a smooth tensor field on M. We're going to say that T, the tensor field, extends continuously if you can find a neighborhood around this origin such that the components of that tensor field then all extend continuously. And so then, and you can show that this doesn't depend on the choice of coordinates by the usual transformation law for tensor components. Right, so the picture would be this. Right, so here's your special point O, and then this is M, right? So you have a function on this space, but then you're trying to extend it continuously to just that point here, right? So for the tensor field, all you need to do is show that there's a neighborhood around that point such that the components of the tensor within that neighborhood will all extend continuously. Okay. So this is the main result. So we're considering this setting. we have a continuous, we have M is equal to the time-like future of some extended spacetime at some origin point, where the origin is a boundary point. And we're going to make these 4 assumptions. So 1, mg solves the Einstein equations with a perfect fluid, u rho p. So that's one of the assumptions we want to make. We want to assume that the integral curves of u have passed endpoint O. So we have this vector field u on our manifold, but we're still going to make the assumption that the integral curves of u all extend to the origin. So what do I mean by that? Right, so here's our origin point. So it's basically the same picture before, but now they can be wiggly. So these are the integral curves of u. I'm not demanding they to be straight lines or anything like that. But one technical assumption I have to make is that these curves are time-like when you include the origin. So of course they were time-like curves within M, but as soon as you include the origin, I need to demand that they are time-like, which ultimately means I need to assume that they satisfy a Lipschitz condition at the origin. It's a technical assumption, so it's not that important. Ricci, rho, and p, I'm going to assume extend continuously to M union the origin. So the functions rho and p extend continuously, and the tensor t, or the tensor Ricci. And I'm going to make a final assumption that the extended spacetime is strongly causal at the origin. And what does it mean? What does it mean for a spacetime to be strongly causal? I mean, it's a very mild causality condition, but you're strongly causal at a point if given any neighborhood u of that point, I can find a neighborhood v of that point, v, such that if I'm a future directed causal curve with endpoints inside v, then that means that the causal curve had to have been inside u. So I have to be like this. I could not. Yeah, I have to be in V, but I couldn't have done this like that. Sorry, did I say it wrong?
I think that one's okay. I think what we can't do is have it go all the way outside U.
Oh, you're right. Yes. Oh yeah, maybe I'm forgetting the definition now, but you're right. You're right. I can't have, this is a bad picture. If I have endpoints in V, thank you. If I have endpoints in V, then I had to have been completely contained in the neighborhood U. I could not have done something like this, or maybe more appropriate, something like that. Essentially, yes. Yeah, thank you. Okay, so these are the 4 assumptions that I'm making, and I'm making this big old spiel that these are non-homogeneous and isotropic versions of Milne-like spacetimes. However, I haven't actually found any spacetimes that satisfy these assumptions that are not Milne-like themselves. So that immediately brings up an open problem. Are there spacetimes that actually satisfy the hypotheses of these theorem but are not Milne-like? And the trouble really is trying to get all the integral curves having passed endpoint at the origin. This is at least what I think the trouble is. Okay. So let me just make a couple of remarks about that, because you could try to maybe consider an initial value problem, right? Say you want to solve the Einstein equations with just the vacuum Einstein equations with just a cosmological constant. You can imagine setting up a hyperboloid of initial data where you do that, right? And then you could perturb the initial data or the second fundamental form so that you wouldn't get something that was exactly like a Milne universe. But then if you look at the co-moving observers, it's not guaranteed that they will come from the origin anymore. So this is I think the part that would be tricky to solve. Okay, so
Eric?
what is the proof of this theorem? So the idea is, so the proof is by contradiction. And so suppose that rho did not equal to minus p at the origin, right? So the conclusion, I'm not even sure if I said the conclusion. The conclusion, right, is that rho at the origin is equal to minus p at the origin. That's the whole point, getting the equation of state to be that of a cosmological constant at the origin. Okay, so assume that this was not true. So suppose rho did not equal to minus p at the origin, then we can write out the Einstein equations So because the Einstein equations are solved by a perfect fluid, you can rewrite this tensor u star times u star as such. And we're doing this in a neighborhood where rho plus p is not equal to 0, right? Because we're assuming that this is not, rho does not equal minus p at the origin. So by continuity, there'll be a neighborhood where it's not equal to 0, so I can divide by it. So that's the point. Now, we assume that Ricci extends continuously to the origin, which implies that its scalar curvature extends continuously to the origin, which will imply that the stress energy tensor extends continuously to the origin, right? So the right-hand side of this equation, is going to extend continuously to the origin, but so then that is going to imply that the left-hand side extends continuously to the origin. But that implies that u star, the one form, extends continuously to the origin, which implies that the vector field itself extends continuously to the origin, right? So under these assumptions, we've just proven that the vector field u extends continuously to the origin, and then the picture you should have in mind is this picture here, because u is the tangent to these curves, right? There's no way that tangent vector field is going to extend continuously to the origin. And this is the contradiction that one should have in their head. And to make that all work, you need to have these assumptions. The integral curves of u have past endpoint O. You need m to be equal to the time-like future of O, but that's actually much stronger than you need. Actually, you just need the time-like future to be a subset of m, and in fact, that's even stronger than you need. You really only need a convexity assumption. If you have a certain convexity assumption, that would have been sufficient. And then finally, also, you need a strong causality. It was a causal assumption that needed to make the whole argument work. And so then, if you have those things, then that implies that u does not extend continuously to the origin. So you have a contradiction, right? Assuming rho does not equal minus p, you prove that u extends continuously to the origin, but you don't have u extends continuously to the origin, so therefore rho had to be equal to minus p at the origin. Okay, so now let me say some applications to inflationary theory. Okay, so many cosmologists argue that the scale factor underwent an era of inflation before the radiation-dominated era, but after the Big Bang. So the picture, and Jerome and Gazelle can correct me if I'm wrong about this, but I think the picture, if you should imagine the scale factor, so if this is tau, and you want to imagine what the scale factor looks like, I think the idea that most cosmologists have today is that it began in some inflationary period where the second derivative is positive, so you're accelerating, right? And then you transitioned through some sort of reheating process to a radiation-dominated era where you're no longer, your second derivative is negative, and then you transition to a dust-dominated era, and then eventually some sort of dark energy kicked in, and then you were accelerating again. So then you went like this. So this is supposed to be what A of tau looks like. And the point is that in the beginning, many cosmologists wanted some form of acceleration in the beginning, because then this would solve sort of certain problems in cosmology, like the horizon problem, the flatness problem, and the monopole problem that David was talking about, Garfinkel was saying last lecture. Okay, so recall Friedman's second equation, right? This second equation right here. So notice that if rho of 0 is equal to minus p of 0, and again, this is all just in FLRW, and the energy density was positive at the Big Bang, then plugging these two things implies that the scale factor is going to be accelerating, right? Because this quantity on the right-hand side will be positive, and this is for values of tau near tau equals 0. And so this is by continuity, right? So having something that begins as a cosmological constant yields something that's accelerating, and this is known as a quasi-de Sitter expansion for the early universe. And so the main theorem can be used to generalize this quasi-de Sitter expansion for spacetimes that are not homogeneous or isotropic. And I think, you know, the big point of this theorem I want to try and make is that, like, you know, if one were to suppose, if one wanted to propose initial conditions for the universe, and one wanted to account for inflation, then this would be something that one should do, because this would be something that would actually force inflation. It's not something that because many cosmologists, you know, to invoke inflation, they assume sort of scalar field potential or something that aligns with more physically what people think physically should happen. But this is more of like a geometrical reason that the scale factor had to accelerate. You had to have come from these geometrical assumptions. Okay, so I want to show how we can do a very similar thing for the spacetimes that satisfy the assumptions in my main theorem. So the divergence of the vector field, so to do that, let's consider FLRW spacetime and just introduce an orthonormal frame where E0 is equal to partial tau, or U, and then calculate the divergence of that vector field, and you'll find that it's 3 times A prime over A, right? So if you set H, which is the Hubble parameter, to be equal to 1/3 the divergence of the vector field U, then it's equal to A prime over A. So many cosmologists just take that to be the definition of the Hubble parameter, is just A prime over A. Doing that, then you calculate the second derivative. It's the second derivative of A, it's just H prime plus H squared. Okay, now let's consider the setting of a spacetime where you just have a time-like vector field U. So no longer FLRW spacetime. So we're considering a spacetime MG that has a unit time-like vector field, and we're going to set H again to be 1/3 the divergence of U. Right? We can always take the divergence of a vector field, and we're going to set H to be 1/3 that, and then we're going to define the average length scale, this math frac A of tau, to be A prime over A equals H. Right? And so this average length scale, which was a term I believe was introduced by Ellis, it reduces to the scale factor in FLRW spacetimes. But here, this is just something that you could have for any spacetime, so long as you have a future-directed time-like vector field. Okay, this then implies that the Raychard-Dury equation gives this expression, and this is just a generalization of Friedmann's second equation here. So here, tau is the flow parameter of U, i.e. the proper time of its integral curves. Omega is the vorticity scalar, and sigma is the shear scalar. And let me just remark that if omega is 0, then the vector field U is hypersurface orthogonal, and then in that case, we have a foliation of manifolds, hypersurfaces, where U is the normal, right? And then in that case, H actually coincides with the mean curvature of these slices. And then it's just a nice happy convenience that mathematicians use H for mean curvature, and then physicists use H for the Hubble parameter. Okay, so so let's consider that setting in mind, and now let's consider the setting of the main theorem, right, where MG solves the Einstein equations with a perfect fluid. So then, if we assume the hypotheses of the theorem, rho plus p is equal to 0 at the origin. So this term will die when you go to the origin, and this term will die when you go to the origin, and then all you're left with is the pressure terms, right? But those can be related back to rho themselves because rho is equal to minus p. And what you find is that the continuous extension of Ricci at the origin is going to satisfy this, right? So in some sense, it begins like an Einstein manifold, right? An Einstein manifold is one where Ricci is equal to a constant times the metric. What happens is that you approach at the origin, you are essentially like an Einstein manifold. Okay, but then the big point of this is that because you have Ricci is equal to this, then if we take the vector field U for points close to the origin, this Ricci of UU is going to be approximately minus 8 pi rho. And so then now if we stick that back into the Raychard-Dury equation, right, then we get this expression. 3a double prime over a is equal to 8 pi rho plus 2 omega squared plus minus 2 sigma squared, etc., right, for points sufficiently close to the origin. Now omega is positive, so we can forget that. If U is a geodesic vector field, which is the case when you are in FLRW, then this term is going to be 0. So let's just say we can ignore that term as well. Then basically what we're saying is that so long as sigma squared is sufficiently less than 8 pi times the energy density, this will yield a generalization of an inflationary era because we will have a double prime is greater than 0. And sigma itself is just a measure. Sigma, so sigma is a measure, is the shear, and for FLRW spacetimes, it's 0. So in some sense, sigma is a measures how not isotropic your spacetime is. Okay, and I think that's it. So thank you, and here are some references.